In this lecture, we learn how to compute the homology of product of two spaces. So say we are given spaces x and y. More concretely, we can take them to be CW complexes. Then we can find the homology of this product x times y via the short exact sequence given to us like this. So this is the nth homology group. So to compute this group, we have to find a couple of direct sums. So first you take homology group of x and tensor with homology group of y such that this r plus s sums up to n. So this n is same as n here. And then you take the TOR of homology groups of x and homology groups of y so that r plus s is equal to n minus 1. So this n is here, you have one index less here. Few words about TOR. So TOR is a derived functor. So we have talked about this in the lectures on homological algebra. Here we just state two properties which we are going to use repeatedly. So the first property is TOR of a comma b is 0 if a or b are torsion free. So in particular, if a or b are integers, this will just become 0. Second property is TOR of z modulo nz comma z modulo mz is just z modulo greatest common divisor of nmz. So for example, say we have TOR of this comma z comma 2z, this will just be again, so because greatest common divisor of 2 and 2 is again 2, and this is what we are going to use in our example. So the example which we are going to do is we are going to take space x as rp2 and y as rp2. So and we are going to compute x times y, so rp2 times rp2, and we are going to use this short exact sequence. So first we need to know what are the homology groups. So the 0th homology group of rp2 is integers. So the first homology groups is z modulo 2z, and higher groups, that is h2, h3, h4 are all 0. So let us now start computing this. So first the 0th group. So for 0th group you have h0 x times y, which we copy right here, and here r plus s have to sum to 0. So we are not considering any negative indices, so it has to be the case that you only have 0 and 0 here, because 0 plus 0 will give you 0. So you have this. Here r plus s has to be equal to minus 1. Since we are not considering negative indices, this term will not be considered, so this will be all 0. So you can say h negative I is all 0 for our rp2. So you put all of them 0. So this short exact sequence now just becomes this sequence right here. So you have an iso here. So h0xy is just tensor of h0x with h0y, but h0x is integers, so this is integers, and x and y are the same space. This is also integers. You can see this right here. So integer tensor with integer gives you integers. So our 0th group is just integers. So now we compute for the h1. So now you have h1 here. This we copy right here, h1. So TOR we have to compute for 0. So for 0, only choice left is h0 and h0 here. So you have h0x here and h0y here. So h0x is integers, h0y is also integers, and these are torsion free. So this is 0 if a or b are torsion free. This we have said before. So this terms becomes 0. So everything in h1 has to come from here. So here we have now 1 here, n is 1. So the two indices r and s which sum up to 1 are h0x tensor with h1. So now you can see 0 plus 1 is 1, and then h1x and h0y, because you have 1 plus 0 is again 1. So this has to match here. So what is h0 of x? So h0 is integers and h1 is z modulo 2z. So this thing is integers and this thing is z modulo 2z. Similarly here h1 is this z modulo 2z, and this is just integers. So if you take integers modulo with z modulo 2z, you just get this. You modulo this, you get this. So our h1 is, so tensor this, you get this, tensor this, you get this. So h1 is z modulo 2z, direct sum with z modulo 2z. Now we want to compute h2. So for h2, we have h2 right here. So this h2 will have to come from some direct sum here. So for direct sums here, you have 0, 2, sums up to 2. You have 1, 1, this also sums up to 2. You have 2, 0, and this also sums up to 2. And for TOR, it has to sum up to 1. So you have TOR of h1, h0. Then you have direct sum with 0, 1. So again, 0 plus 1 gives you 1. 1 plus 0 gives you 1. So here, now first look at the TOR terms. So for the TOR terms, you know the h0 term is integers. So this is integers. Here again, this is integers. So once you have integers, this will become 0. So this becomes 0 and this becomes 0. So everything here comes from these three terms here. Now we know h2 is 0. So this is 0. Here also this is 0. So everything is coming from this term. So h1 tensor with h1. And h1 is z by 2z. Then tensor it with z by 2z. You get. So this is nothing but z by 2z, which comes from here. Tensor with z by 2z. And you get z modulo 2z. Now we compute h3. So for h3, first focus on this. Now r plus s has to be 3. So our indices are going to be 0, 3. Then you have 1, 2, 2, 1. So 0 plus 3 is 3. 1 plus 2 is 3. 2 plus 1 is 3. And finally you will have 3 plus 0, which is again 3. So but we know 2 and higher are all 0. So this is 0. This is 0. This is 0. This is 0. So everything becomes just 0. So this is actually true for now r plus s equals to 4, 5 and so on, and you can prove this via induction or directly using combinatorics. So now we are just left with the TOR term. So nothing is going to come from here. Everything is going to come from the TOR term, but TOR is going to be r plus s is 2. So you have h0, h2, sum is 2, h1, h1, sum is again 2, 2, 0, sum is again 2. So so 0th is integers. So this is integer, this is integer. So this will become 0, this will become 0 because of our first property. So integer, you get TOR is 0. So everything in the TOR comes from these two terms. And these two terms, h1 x and h1 y, they are same. There is z2z, which is precisely what we have written here, and this is z2z, z modulo 2z, and that's what you get here. So you get h3 as z modulo 2z. And for higher, h4 and higher, everything would be 0 because this term would be 0 and this term would be 0.